Hi class. Next we're going to consider what's known as the WKB method, which again is a way of solving this singular perturbation problem, this differential equation, where the order of the equation changes in the limit where the parameter epsilon goes to 0. In this case, we're going to take the case where there's no linear term, where a of x dy dx goes to 0. And for convenience, instead of the small parameter, defining a small parameter to be epsilon, we'll call it epsilon squared for reasons you can probably guess, because as we showed, the variation is really determined by the square root of the parameter in front of d squared y by dx squared. Also, to make contact with my notes and the way it's discussed in Bender and Orszag, I'm going to call b of x, in this case capital Q of x, just notationally, and we'll talk about different examples. We'll talk about examples with boundary conditions and with initial conditions for solving this equation. Now, the problem is we expect that this term is going to give us rapid variation, but unlike the case where a of x is non-zero, we expect that rapid variation to be true potentially all the way throughout the region we're interested in. And we're going to isolate that rapid behavior by, instead of solving for y, solving for s, where y of x is e to the s over delta, where delta is a small parameter whose value I'm going to determine by dominant balance to try to figure out how to approximate the equation consistently. So if you plug in y is e to the s over delta, the second derivative becomes basically s prime squared plus s double prime. And if you follow through with the powers of epsilon and delta, there's an epsilon squared over delta squared in the first term, there's an epsilon squared over delta times s double prime in the second term, and the last term just is q of x times e to the s. The e to the s is common to all the terms, and therefore you get this nonlinear ordinary differential equation for s. Normally, you'd think that was actually a step backward because it's a nonlinear equation instead of a linear one. However, dominant balance would tell you that in general, if you've been able to take out correctly the rapid variation, control the rapid variation of the function by this transformation, then the function capital S, it and its derivatives are of order 1, so s prime squared and s double prime should be of order 1. If that's true, then the first term will always dominate over the second term, because the first term has an extra power of 1 over delta. Therefore, you expect this term to dominate over this, and dominant balance is given by equating this term with the term capital Q, the other term of order 1 in the equation, with this term being subdominant. So epsilon squared over delta squared should be of order 1, or delta is order epsilon. And that's why we chose the parameter in front of d squared y by dx squared to be epsilon squared. Now, we're going to assume that we have an expansion for s in powers of delta, and we're going to solve this nonlinear differential equation order by order in delta. Again, this expansion is not a convergent expansion. It's going to be an asymptotic expansion. The leading term is just s, if the leading term comes from this term, s0 prime squared plus q of x equals 0, where s0 is plus or minus the integral of the square root of q, square root of q of x prime dx prime. Again, this x prime is just for us to keep track of the dummy variable of integration. If we plug the first two terms into the equation to get a better approximation, here's the s prime squared term, here's the s double prime term, here's q. We've arranged s0 prime squared to cancel q, so the remaining term of order delta, the next order approximation, is 2 s0 prime s1 prime plus s0 double prime equals 0. This can actually be solved completely. This is remember, s0 prime is actually given to us. It's an equation whose value we know from here. So this is actually just a first order differential equation for s1. That equation is s1 prime is minus a half s0 double prime over s0 prime, but actually that's an exact differential, minus a half of log of s0 prime. So we integrate that. S0 prime, we know, is equal to the square root of q. So S1, up to an overall constant, there's an arbitrary constant here in principle, is minus a quarter log q. So the most general WKB form of the solution of this equation, again, this is true for an equation which has a small parameter here and no linear term, is some arbitrary coefficient q to the minus a quarter when I exponentiate. There's a delta in front of s1, but that cancels because I'm actually taking e to the s over delta. So I get a q to the minus a quarter exponential 1 over delta. Delta is epsilon. Integral up to x square root of q dx prime plus c2 q of x to the minus a quarter exponential of minus 1 over epsilon integral up to x square root of q of x prime dx prime. Notice that you get two linearly independent solutions, just as you should for a second order ordinary differential equation. So we have two solutions that we know. We can now apply, for example, initial conditions. So suppose y of 0 is a and y prime of 0 is b. Then just plugging in, if I choose my lower range of integration to go from 0 up to x by adjusting c1 and c2, then I get this equation for a, q of 0 to the minus a quarter c1 plus c2 is a. And if I take a derivative, the derivatives can either take derivatives on the outside on the q's, which gives me this term, or I can take them inside on the exponentials, which gives me that term. The sum of those has to be equal to b. For example, if you take the special case a is 0 and b is 1, you find the general asymptotic form of the solution goes like epsilon q of x, q of 0 to the negative a quarter times the sinh of the integral from 0 to x of q, square root of q of x prime dx prime. Now, where is this WKB approximation valid? This is the kind of asymptotic expansion that we're looking for. The exponential of 1 over delta, sum on n, delta to the n, s to the n. So we certainly need each successive term in the expansion to be smaller than the preceding term. So 1 over epsilon, right, delta equals epsilon. 1 over epsilon s0 had better be greater than s1. S1 had better be greater than epsilon s2, etc. But actually there's more than that. If we truncate at nth order, this is the next term, epsilon to the n plus 1, Sn plus 1 of x. That's going to be a term we're leaving out in the exponential. If this is going to be a good approximation, remember we're exponentiating it, then it had better be true that this is also less than 0. So it's not sufficient just for each term to be successively smaller, but the term that you leave out had better be small in and of itself. So the truncation error, if you think about it, is of order e to the epsilon n plus 1, s to the n, Sn plus 1 over epsilon. So we need this whole term to be equal to be small. Let's apply this. Let's apply this to compute the asymptotic expansions of the Airy function. D squared y by dx squared equals x times y. Now, we're actually going to set epsilon equal to 1 here. There's no term out in front. Epsilon squared up here is equal to 1. Why might this work? The reason it might work is if I think about this right-hand side here, the x times y term, if I think of y as being of order 1, I could think of putting the 1 over x on this side. And as x gets large, the term, the effect of the second order derivative is going to get smaller and smaller. So even though there's no epsilon here, and epsilon is 1, in the limit x goes to infinity, we expect that we should be able to derive an asymptotic expansion for the solution of this equation. This is the Airy function that I discussed in class earlier. If we just apply, q of x here is equal to, q of x is equal to minus, I see. Actually, I should have put a minus sign here. Sorry. There's a minus sign, there's a minus sign, there's a minus sign. Q of x is equal to minus x in this case. And so S0 is plus or minus the square root, if you just plug in, square root of x prime dx prime. So the integral is 2/3 x to the 3/2. S1 is just minus a quarter log x. If you compute, you can go to the next order, you'll find S2 is 5 over 48 x to the minus 3/2. And notice that as x gets large, S2 is numerically smaller and smaller. So for that reason, we can truncate the WKB approximation with just the first two terms. And what we find is that those solutions have two forms. There's c plus and minus x to the minus a quarter times the exponential of plus or minus 2/3 x to the 3/2 plus a power series in x. If I include this term, the next term, the corrections are going to be of order x to the minus 3/2. That x to the minus 3/2 would have been the exponent, but I can expand it out, and that'll tell me that there's essentially a power series correction in powers of x to the minus 3/2. What happens as x goes to minus a half? Well, all that happens is x to the 3/2 instead becomes I times x to the 3/2, x to the minus a quarter where I put the absolute value of x here. X to the minus a quarter becomes the absolute value of x to the minus a quarter, etc. And I get two forms for the Airy function. I get oscillating forms for the Airy function as x goes to minus infinity. The two conventional solutions for the Airy function are called ai of x and bi of x. Ai of x vanishes exponentially in the positive x direction, and then you just continue it backward, and that defines the oscillatory behavior here. And so this is the determining form of the Airy function as x goes to positive infinity. The bi is the function that blows up exponentially as x goes to positive infinity. Again, both of them oscillate for x negative. Next time, we'll use the Airy function to actually do semi-classical quantization in quantum mechanics.